Okay, good evening and good morning. I'm Tomokazu Morota from the University of Tokyo. We have been working on defining the scientific objectives for a sample return mission utilizing a pressurized rover. We have also been evaluating suitable explanation site and developing in-situ observation instruments necessary for sample return. In this presentation, I will focus on the scientific objectives and the potential explanation site, and the strategy for selecting samples on the moon will be presented in the next talk by Nagaoka-san. Next slide, please. Yeah. What we are aiming to achieve with a future lunar sample return mission comes down to two main science goals. The first is to constrain the formation conditions of the Earth-Moon system. The second is to reconstruct the early impact history of the solar system. They represent high priority science goals that sample return missions in the Artemis era are uniquely positioned to address. Yeah, I will now go into more details on each of these objectives. Next slide, please. Yes. One of the key observables for constraining the formation conditions of the moon is its bulk composition. And one of the most direct ways to determine the bulk composition is to return and analyze pristine cluster rocks crystallized directly from the lunar magma ocean. By analyzing the isotope and the volatile content in such rocks, we can infer the composition of the magma ocean itself and estimate the abundance of volatiles in the lunar interior at the time of cluster formation. Through these types of observations, we aim to address key questions such as what materials was the moon made from, and under what thermal condition did it form? Yeah, next slide, please. Yes. Candidate rocks formed directly from the lunar magma ocean have been identified by remote sensing observations. So data from the Kaguya multiband imager liberaled rock exposures with nearly 100% plagioclase by volume, what we call peerless anosocite. These peerless anosocite were widely distributed at depths of several tens of kilometers, implying a globally extensive thick anocitic layer. This thick and widespread structures suggest that these rocks may be direct crystallization products of the lunar magma ocean. To determine the composition of the lunar magma ocean, it will likely be essential to return samples from these peerless anosocite unit. Yeah, next slide, please. Yes. Another major science objectives is to better understand the early impact history of the solar system. Due to that, we need to determine the ages of large impact basins of the moon. So about 50 impact basins have been identified on the moon, but it is not necessary to date all of them. Thanks to previous geomorphological and stratigraphic analysis, we already have a well-established framework for their relative ages. So therefore, obtaining absolute ages for a few key basins would allow us to test the rate heavy bombardment hypothesis. In particular, the SPA basin, the oldest basin of the moon, and the Nectaris basin, which is widely used stratigraphic marker in lunar geology of critical importance. Yeah. The age of the Imbrium Basin, one of the youngest large basins, have already been determined from Apollo samples. Thus, if we can determine how much older SPA and Nectaris were relative to Imbrium, we can assess whether there was a temporal spike in the impact flux at 3.9 billion years ago. Yeah, next slide, please. Yes. Now I'd like to move on to discuss where on the lunar surface we need to explore in order to address the scientific questions I've outlined so far. So we are interested in exploring low to mid latitude regions, but we recognize that the initial target area for the pressurized rover will be lunar south polar regions. So therefore, in the following section, I will focus on the scientifically interesting areas around the South Pole. Thus, South Pole region is thought to be a complex mixture of materials, original highland crust from the South Pole, SPA ejected and the impact deposits from the subsequent basins and craters. So there are also possibilities that mafic rocks currently exposed within the SPA basin interior have been transported and mixing into this region. So currently, as shown in this figure, we are using Kaguya multiband imager data to search for plagioclase-rich crustal materials and to map the distribution of mafic components. So previous geological studies of the South Pole have identified PRS anosocite around Shackleton craters, and as shown in this figure, so plagioclase-rich materials can also be detected around Shackleton. So therefore, this area is considered a promising target for sample return mission in the lunar polar regions. Next slide, please. Yes, one of the important explanation target near the South Polar region is the Schrödinger Basin. Within the central peak ring of the basin, both PRS anosocite and olivine-rich rocks have been identified. So this ring is believed to have originally formed deep within the crust and was uplifted and exposed during the basin formation. As such, it represents a key site for understanding the composition of structure of the crust in the South Pole region. Next slide, please. Yeah. As mentioned earlier, the formation age of the SPA basin represents one of the most critical information for constraining the early impact history. The central depression region within the SPA basin is composed of high calcium pyroxene-rich materials, which may represent remnant of that impact melt sheet. A sample return from this central region could potentially allow us to determine the formation age of the SPA basins. Next slide, please. Yeah, its final slide. We are currently developing in-situ observation instrument to help identify rocks that preserve primordial information on the lunar surface. Surface, and our goal is to have these instruments mounted on the pressurized rover and to utilize the rover for the sample collection in the future missions. The strategy for selecting primordial rocks on the moon and using these instruments will be presented in the next talk by Nagaoka-san. Yes, thank you very much.